Hello everybody, it's Tharun. Welcome to your 19th tutorial in the Signal System and Control course. In this tutorial, I'll start with Unit 6, which is sampling. Okay, in this unit, I'll teach you the connection between continuous time and discrete time signals. Okay. So now let's start. First of all, we'll talk about sampling theorem. Okay, which shows us the complete representation of a continuous time signal by creating small samples of it. Okay, so and the next thing which we'll see is the sampling and its reconstruction. Okay, it is implementing continuous time systems and then processing those continuous time systems under the discrete time signal technology using the sampling. Okay, so you can describe efficient discrete time processing by this block diagram. Okay, first of all, you have passed an analog signal or continuous signal x of t, okay, which passed through analog to digital converter or continuous to discrete converter, which makes the signal x of t x of n, and then with the discrete time processing we get our output yn. Okay, and then again it is passed through digital to analog converter now, or discrete to continuous converter, and then we get the desired output yt. Okay, now these are the few things which I will cover in this unit. Okay, first is the sampling theorem, which I will teach you in this unit, then the reconstruction of the sampled signal, and then the third thing is the effect of undersampling, which is also called aliasing. Okay, and the fourth thing which I am going to teach you is discrete time processing of continuous time signal, and then the sampling of discrete time signals. Okay, so now let's get started with the sampling theorem. The sampling theorem, its objective is that we are going to represent a continuous time signal by creating its samples. Okay, so we are having a continuous time signal xt like this, and we have created some samples of it. Okay, these are the just wait, these discrete lines. Okay, these are the points at which we have divided our continuous time signal into samples. Okay, so what is the observation with this sampling? Okay, an infinite number of signals can generate a given set of samples. Okay, and we need additional constraints on continuous time signals to process them as discrete time signals. Okay, so first is impulse train sampling. Okay, it is a representation of sampling of continuous time signal. Okay, as we all know that the sampling property of unit impulse xt into delta of t minus t naught, which is equals to x of t naught into delta of t minus t naught. Okay, so in the impulse train sampling, we will sample the signal at regular intervals spaced by capital T. Okay, which is our periodic impulse train, and the periodic impulse train p of t is summation n equals to minus infinite to infinite delta of t minus nt. Okay, and here it is the graphical representation of the impulse train. Okay, so the mechanism for impulse train sampling is that we'll multiply our signal, continuous time signal xt, with our impulse train. Okay, to get the sampled signal. Okay, which is represented by this manner. Okay, xp of t, xp of t, which xp of t is equal to x of t into p of t. So the value of xp of t will be summation n equals to minus infinite to infinite x of nt delta of t minus nt. Okay, so amplitude of the impulse, these impulses. Okay, as you first of all, as you all can see that xp of t is also a impulse train. Okay, with x of t as its amplitudes. So the sample of xt will be the amplitude of this the amplitude of impulse train xpt. Okay, here p of t is sampling function, capital T is sampling period and omega s is the sampling. So now let's see the illustration of the above impulse train sampling which I have told you. Okay, I've taken the signal xt, multiplied it with the signal pt, okay, which was our impulse train, and then we get our sampled signal xp of t. Okay, so now let's see this graphically. Okay, we are having our signal xt like this. Okay, xt is this, which is continuous, and it is our impulse train pt. And when we multiply these both signal, then I will get only the peaks at these points only. Okay, so now let's see at 0 the peak is this. So in the continuous time signal I will get this point only, so I will get a peak like this, and then similarly you can see for the rest. Okay, and when you join these the peaks of these samples, you will get your continuous signal. Okay, so for sampling function you can also refer to the Fourier transform unit, where I also mentioned that sampling function. Okay, so this was our sampling impulse train. So if I find the Fourier transform of this function, okay, which will be this, okay, which will be equals to summation n equals to minus infinite to infinite e to the power minus j n omega t, okay, which is periodic with 2 pi by capital T. So now let's see the modified spectrum which is in the what we can say in the frequency domain. Okay, y of j omega is equal to p of j omega into sinc omega t upon 2 pi. Okay, and its Fourier representation or Fourier transform or vice versa is y of t equals to p of t convolution 1 upon capital T rectangular small t upon capital T, which is equals to 1 upon t. So we are taking this system where yt is pt into this rectangular function, okay, and its value is 1 upon t. So I Fourier transformed it here. Okay, so y of j omega will be 2 pi by capital T into delta of omega. Okay, so p of j omega is determined except for omega is equal to 2 pi by capital T, 4 pi by capital T. Okay, so in the periodic continuation you can see that p of j omega will be summation n equals to minus infinite to infinite 2 pi by capital T delta omega minus n 2 pi by capital T. Okay, or I can take out the 2 pi by capital T outside, and here I have replaced 2 pi by capital T as omega s. Okay, so there are few properties in the spectrum of sampled signal. Okay, so xp of t is a sampled signal which is equals to xt into p of t, and which is this expression. So if I Fourier transform xp of t, it will be xp of j omega, which will be 1 upon 2 pi x of j omega convolution p of j omega, and the expression changes here by 1 upon t is outside because of the Fourier transform of delta function, and it will become x of j omega minus n omega s. So now let's see one illustration with this example. Okay, we are having x of j omega like this. Okay, and I am convoluting it with this impulse train with 2 pi by t as its amplitude. Then I will get xp of j omega like this. Okay, so we observe from this illustration that the superposition of n omega s and scaled 1 upon t replicas, which means that in our original x of j omega signal there was only one spectral lobe. Okay, this is a spectral lobe. Okay, but in the sampled signal xp of j omega we are having replicas of it. Okay, and it is periodic with omega s is equal to 2 pi by capital T, and it's shows the duality property. Okay, where periodic signals Fourier transform is impulse train spectrum and sample signal is Fourier transform is periodic spectrum. Okay, so now let's reconstruct our sampled signal with the help of low pass filter. Okay, so I am having a low pass filter h of j omega. So when I pass a sampled signal through the low pass filter, I'll get xrp, okay, which is the reconstructed signal. R stands for reconstructed here. Okay, so first case we are having omega s is greater than 2 omega m. Okay, omega m is the message signal frequency and omega s is the sampled frequency. So the reconstruction filter h of j omega is defined like this. It is equal to t for mod omega less than equals to omega m, and it is 0 for mod omega greater than omega s minus omega m. Okay, which is this region, and other condition we don't care. Okay, so what I'm trying to do is that I've got this signal which is a replica of our original signal. I want to extract out only the center part of this, so I have taken a low pass filter which is defined like this, which will only pass the central part of this sample signal. Okay, then I'll get my original signal back, and then xrt will be equals to x of t. Okay, so now let's see the second case where omega s is less than 2 omega m. Okay, so in this case what will happen, the sampled signal will look like this. Okay, it has overlap, as you can see here that it originally was like this. Okay, as you can see here, and but it has overlapped, so it took the shape of this graph. Okay, and this effect is called aliasing, and if I pass it to the low pass filter which I have defined in the above case, okay, then I'll get the reconstructed signal which will not be equal to our original signal. Okay, so now let's see the sampling theorem by the statement. Okay, the statement says let xt be a band limited signal where the x of j omega is 0 for mod omega greater than omega m. Then xt can be uniquely determined by its samples x of nt, where n belongs to natural numbers. Okay, if omega s is greater than 2 omega m, where omega s is 2 pi by capital T. Okay, these are the constraints for the sampling theorem. So now let's talk about the reconstruction of xt from the samples x of nt. Okay, we have generated a periodic impulse train or the impulse to signal xp of t. Okay, when we pass the impulse train to the low pass ideal low pass filter with a gain t and its cutoff frequency omega c, which lies between omega m and omega s minus omega m, then there are few conditions in that case. Okay, one which I told you earlier is that when omega s is greater than 2 omega m, then it will be just normal reconstruction and we'll get our original signal back. Okay, and second condition is critical sampling, where omega s is equals to 2 omega m. Okay, and which is also called Nyquist rate, and here fs will be 1 upon t, which will be omega m upon 2 pi. The next condition is undersampling, which I have also told you, which lies in the case when omega s is less than 2 omega m. Okay, so there is a difference in the things work in the real world, which I have told you. Okay, which is there because there is no possibility to create an ideal low pass filter. So in practical applications, the ideal low pass filter would be replaced by a non-ideal filter, which will lead to some discrepancy between xt and or reconstructed signal xr of t. Okay, so now let's see the reconstruction in a practical manner. Okay, and this practical reconstruction, okay, or I can say I'll define both the ideal and non-ideal reconstruction in the next tutorial. So thank you guys for watching. I'll see you in the next tutorial.